Hello everyone, welcome back to another discussion dynamics. Today we will continue momentum of rigid bodies, and we will focus on this subtopic, angular momentum of rigid bodies. So I will start our discussion with a brief lecture review, and then we will do two examples. Without further ado, let's dive straight into it. So this is a brief lecture review I prepared. So today I will just derive angular momentum equation for you, and we will use it today like 3 or 4 times. But before I show you the equations, let me draw something. Let us consider that we have a rigid body, and our rigid body has mass and moment of inertia about point C. And what else? Maybe our body can be pinned here at point A. Why not? And also, since we are in momentum chapter, I think we should also know some information about the velocity of the body, right? So this will be our velocity of the center of mass, and also our body will be rotating with omega. Yeah, I think that's all. Okay, so there are two versions of angular momentum equations. One is more general and the other one is a little bit simplified. I'm going to show you two of them, okay? So if you would like to find angular momentum of that body about point A, vector-wise, you should go for the following expression. I think this is R CA times MVC plus IC omega, right? This is the most general expression for angular momentum. However, our body is pinned as well. This is a pin. So we can also go for the other one. We can also express our angular momentum in with such expression, IA omega, where naturally IA can be calculated using parallel axis theorem. MD squared, IC plus MD squared. And I think I forgot to put this vector on the board, but I think that you all know that this vector is here, RCA, and our D, this D, is basically the distance, the length of that vector. So our D will be probably here. Okay, guys. So these are the two most general equations for angular momentum for 3D motion. However, this semester we talk about 2D motion, right? We talk about planar motion. So I will just show you the simplified versions of them, okay? Actually, I'm just going to show you the z component of these vectors. Okay, so this is the z component of that vector. So h can be expressed as mvc times d plus ic omega. That's it. And I think that there is a little typo on the board because I believe that our vc rotates in a negative fashion about point A, right? I believe so. Yes, so I should put minus in here and minus in here. But also our body is pinned, so we can express this h as minus ia omega. And I noticed one more typo on the board. Of course, I forgot about the subscript next to h. Please put a in here. A in here, A in here, A in here, and A in here. These are angular momentums about point A and not any other point, okay? Not point C, for example. This is angular momentum about point A. Okay, and with this brief lecture review, I would like to start working on some examples unless there are questions. I don't see any, so let's see how to use these equations. Let's do example number 1. Here is example number 1. So as usual, please take a couple of seconds to read and understand the problem statement before we start our solution. Okay, so what do we have in here? We have 3 bodies. We have a bar that has mass m and length L. We also have 2 disks, and each of them has mass m and radius r. And they are located at point B and point A. I think I forgot about point A as well. A is here. Okay, and our disks have initial angular velocity, omega 0. And that also, the authors of that problem told us that there is no friction in here. No friction at point C. But there is friction at point B and at point A. And due to that friction present at point B and point A, basically our entire system will start rotating, right? Because we will observe a transfer of the motion, transfer of the momentum from these disks to the entire system, right? Until the disks stop eventually. Okay, I think the problem statement is clear. Oh, maybe one more thing. Please look at that sentence. Motion is in the horizontal plane. That means that our G acts into the page. Our G acts in this direction. Okay, let's start our solution. And I will start it with momentum diagrams, okay? And I think that after you see these momentum diagrams, the problem statement will become even clearer. So these are my momentum diagrams. Momentum diagrams, and I just would like to show you what happens at time instant t1, at time instant t2, and also between these 2 time instants. Okay, so let me do this drawing very quickly. Okay, so here we have mass and length. Here we have mass and radius. And I think that this is point B, this is point C, this is point A. Omega 0, omega 0. Okay. So after a couple of seconds, our system will start rotating a little bit. This way and this way. And after even some more time, our system will be even more tilted. And in here, disks will stop rotating about their own centers of mass, but instead our entire system will have some omega final. And they ask us to find it actually. Okay, guys, so what do we have in these diagrams? We have situation at the beginning, situation in the end, And in here, I will just show you what happens in between. I will just show you what impulses act on our body. So what external forces act on our body? I think that definitely there is mg, but it doesn't play much role in this problem because we will have mg acting this way, mg acting this way, and mg acting this way. Mg, mg, and mg. But there is also a reaction force at point C. We'll have cy and cx. So indeed, these are all the forces acting on the entire system. And I would like to underline the term entire system, because in here you clearly see that we consider the motion of the system. We do not care about what happens with each body individually, right? Okay, guys, so let's integrate our forces. Let's integrate our forces. And I would like to ask you one more question. I think that the momentum of our system, the angular momentum of our system, is preserved about one point. What's that point? C. No, it's okay. C. And why C? Okay. I need more dynamics answer. The only external force acting on the system is acting on that point. Yeah. This is, yeah. But that force comes from the pin, so probably this is what you had in your mind. Yeah. Okay. Yeah, that's true. This is the reason. Yeah. So the only external force, a reaction at point C, is acting at point C naturally. That means that the momentum of the entire system is preserved. Please observe that momentum of each of the bodies, each of the individual bodies is not preserved. Yes, because for example, our disks, they stop rotating about their own center of mass. Yes, but we don't care about them individually. We just care about the entire system, and the momentum of the entire system is preserved. Let's write it down. Angular momentum of the system is preserved. Of the system about point B, of course. About point C, sorry, about point C. Okay, so I can basically write HC initial is equal to HC final. And that problem basically boils down to finding these two quantities. Let's do it quickly. So we can do first our HC initial. And we can decouple it into HC initial of bar plus HC initial of disks. Okay, guys, question to you. Does bar do anything in the beginning? Is bar moving? No, so it's 0. That was fast. So now let's focus on disks. HC init of disks. Please observe that these disks, they move exactly in the same way. So do you mind if I just find angular momentum for one of them, and then we just multiply it by 2? Let's do it. Let's maybe focus on this disk, on disk at A. So what can we do? What can we go for in here? We can do, maybe we can go for the first angular definition. So we can go here for MVA times some distance plus IA of the disk times omega 0. Okay, guys, what distance I should put in here? This should be the distance between point C and point A. So this distance is going to be L half. But actually it doesn't matter, right? Because what's the velocity of point A? Point A does not move anywhere, right? Point A belongs to the bar. So this is 0. That means that we can get rid of this component. And by the way, is omega 0 rotating in a positive fashion or negative fashion? Negative. So I made a little typo. Minus in here. Right? Okay. So we will basically end up with minus 1/2 mr squared omega 0. And as I promised, I will multiply it by 2 because we have 2 disks. Times 2 times 2. So the actual answer is minus mr squared omega 0. Okay, so I think that we found H initial, right? So our HC init is minus mr squared omega 0. So 50% of the problem done. Let's do the remaining 50%. Let's do HC final. And again, HC final of bar plus HC final of disks. Okay, I think I will steal that drawing from here. Oops, gonna be here. So let us focus on HC final of bar. So bar is pinned at point C. I'm gonna go for the second definition of our momentum. So this will be IC bar omega final negative. And in here I can just write minus 112 ml squared omega final. Okay, now let's focus on disks. HC final of disks. And the story is the same. I will just focus on this guy at A. And at the end, in the end, I will just multiply the answer by 2. Okay, just to find the momentum of 2 disks. So in here we can actually go for. In here I just would like to show you how to find that angular momentum using 2 definitions. Okay, if you don't mind, I will just switch the board for a second. I would like to start with this expression, and then I will go for this one. So let's do it. So if we do that, we can just express our IC of the disk. And you can see that the disk rotates with the entire system, right? So I can just put in here omega final, negative. Parallel axis theorem, IC of the disk is equal to IA of the disk plus ml half squared. So this will be equal to 1/2 mr squared plus 1/4 ml squared. And this is equal to m 1/2 r squared plus 1/4 l squared. Okay, guys. So this is the moment of inertia of one disk minus m omega final 1/2 r squared plus 1/4 l squared. Of course, times 2 times 2 times 2 disks. So we will actually end up with m omega final r squared plus 1/2 L squared. I hope I didn't make you too confused. Yes, are there any questions? Even if you don't have them right now, you can ask them later, no problem. Okay, but let's use second definition, okay? So I will show it to you on the previous board. So this definition. Now I'm gonna go for this definition. So in here I can actually write m VA times L half. Plus, and by the way, that VA is in here. And since this is basically that point A belongs to the bar, so I can actually say that our VA is equal to omega final L half. And this is negative, yes? Again, aha, so minus in here, minus in front of it. Plus IA of the disk times omega of the disk. Question to you guys. Is our disk rotating in any sense? It is rotating, yes? It is rotating, yes. So I see that some of you are just saying no, but this is actually not true, you know, because our disk would not rotate if each and every point of that body experience such trajectory. So our disk does not translate only. Do you see that? That point, for example, experiences such trajectory. That point experiences such trajectory. The point that is further from C experiences such trajectory. That means that our body is indeed rotating with omega final. Believe me or not. But omega of our disk is actually omega final. Another way to look at that problem is that, please observe, guys, that actually at the final time instant, that system is one rigid body. These disks do not move relatively to the bar. It is one rigid body. Yes. So that means that omega f of each of its components is that omega, the angular velocity of each of its components is omega final. Okay. Yes, Olivia. They are spinning. Yes, Olivia, they start spinning about its own center of mass. They do not rotate relatively to the bar, but they are still rotating. That's abstract. I know that it's abstract. When I was learning that, I was like, what? No, but it is actually true. Please listen to my previous answer. So that body is a rigid body. You see, it's not relatively to the bar. That system is like one rigid body. Okay. So that means that each component of that system has actually omega final. It's okay. That's my answer. Think about it and we can talk about it later, okay? One typo, negative, yeah? So that was actually my point of showing you these two definitions, because that was the most confusing part for me when I was learning about angular momentum. Okay, guys, so let's see if we end up with the same answer. Let's see. So in here, we should have minus m omega final L squared divided by 4 minus 1/2 mr squared omega final. So this is equal to minus m omega final L divided by 4 squared plus 1/2 r squared. Times 2, because we have two disks. and we'll end up with minus m omega final 1/2 L squared plus R squared. So I don't know what you think, but in my opinion, we obtained the same answer. Okay, so my goal in here was to show you how to use these two expressions. And correct me if I'm wrong, but is it the end of the problem? Did we find, I think we found everything, right? Yes. Okay, so H final is basically this expression plus this expression. And I think we can even simplify it. If you simplify that, you will end up with minus 7 divided by 12 L squared plus R squared plus R squared M omega final. Okay, so we found H initial, we found H final. So now let's equal them to each other. So what was the first one? The first one is here, I believe. This is our H initial. And this is equal to what we just found. Okay, so I think that a couple of things simplify in here. I think M simplifies, these minuses will simplify, and I think that we are ready to find omega final. Omega final is equal to omega 0 R squared divided by 7 divided by 12 L squared plus R squared. This is the final answer. Okay, time for questions. Okay, what do you think of this problem? It is digestible, yeah, but you must probably look at it one more time. Yeah, I mean, this is what I would do. I would never understand it, especially while listening to such guy like me. Yeah, I would go home and do it one more time, just to make sure that you understand it. Questions or example number 2? Okay, no questions. That means example number 2. Okay, here it is. Here is example number 2. So as usual, please take a couple of seconds to read and understand the problem statement before we start our solution. Okay, so what do we have in here? We have only one body. We have our box that has velocity v0 and it goes down the incline on conveyor 1. We know that the side of our box is A. We know that incline has theta of 15 degrees. And what else do we know? Aha, we know that our box will eventually hit that pivot, right? And it will just rotate until it finds its destination at conveyor C. Okay, so that's an interesting problem because we basically in here we will just figure out how to transfer translational motion, yes, along this trajectory into a rotational motion about point B. I think that will be an interesting problem. To be honest, I really like that problem. So let's solve it. Yeah. So, but before we solve it, let's see what we know. We know mass. We know A. If you look at the engineering tables, you can find that IE of the box, or in here we have just one body, so I will just call it IE, is equal to 1 divided by 6 MA squared. What else do we know? We know theta, that is 15 degrees. I think that we know G. However, I will prove you that it does not play any role in that problem. And that's all. And they ask us to find V0 minimal. The minimal V0 such that our box can actually rotate. Okay, guys. So I think that we will start with a hit because our body will hit that pivot. So let me draw some momentum diagrams first. Momentum diagrams. Okay, so this is our situation at the beginning. We have our box going this way. Okay, and I will copy this drawing twice, okay? I'll copy it here, and I will also copy it here. So on the first drawing, I will just show you what happens before the impact, okay? So at time instant t1. Here I will show you what happens at time instant t2, after the impact, right after the impact, and in here I will just show you what happens in between. Okay, so what is our momentum before? I think that our body just goes along this trajectory. And it does not rotate at all, yes? It just translates along that trajectory. In the end, B will become our pivot point. So we'll have omega-2 about B. And in the middle, I will just show you all the forces acting on our system. So we definitely have mg acting here. And we also have one external force acting on our system, which is reaction force at point B in arbitrary direction. We don't know the direction of that force. Maybe in this direction, I don't know. Okay, let's integrate our forces from T1 to T2 dt. Okay, guys. I again would like to claim that momentum is preserved about certain point. However, I cannot do it without one assumption. So right now, my goal is to prove you that actually mg can be neglected in that problem. And this is my reasoning. So basically, I would like to define delta t, that is t2 minus t1. And I just want to let you know that this goes to 0. In other words, the duration of that impact is very short. Indeed, the impacts are very short. Yes? They are like 10 to minus 3 seconds, 10 to minus 6 seconds, maybe. I don't know the exact number, but my guess would be that they are somewhere there between 10 to minus 6 and 10 to minus 3. And basically, that integral from T1 to T2 of mg delta t, this will also go to 0. Because we can always choose T1 and T2 that are so close to each other that basically the impact of mg on our system will be negligible. Is that clear? Just to give you some numbers, I think that, in my opinion, force B, so that red vector, will be 1 million times longer than mg. Okay? During the impact, force B will be, I believe so, that it will be 1 million times longer than mg. That's why, let's forget about it. Let's forget about mg. And you can do it for every impact, not only for this problem. For every time you see an impact, forget about mg. Okay, with such assumption, I think our momentum is preserved about certain point. Which point is that? It's louder. B, exactly. For the same reason as before, because the only external force is acting at point B. Thank you, Olivia. Okay, let's write it down. Angular momentum preserved about point B. Okay, so I think that again we can write down HB, HB maybe before is equal to HB after. Yeah, like before the impact, after the impact. Okay, so let's find these two guys then. So what can we tell about HB before? I want to go for this definition. It will be MVE times some distance plus IE omega 0. As I mentioned earlier, our body just translates. Our body does not rotate at all. This is 0. And this distance here will be naturally this distance. This is a half. So I can put a half in here. Okay, guys, so in here we'll have 1/2 MVEA. Okay, 50% of the problem done. Now HB after. Okay, so the drawing corresponding to this equation is on the in the top right corner. So in here we just have a pivot about point B. So I'm gonna go for the other definition of our problem, okay? Of our momentum. So in here I will just write IB of the box omega 2. And this is positive or negative, by the way? This is positive and the previous one was positive. Great. Okay, parallel axis theorem. So in here we have to just write IB box that is equal to IE box plus M some distance squared. And the distance between point B and E is obviously this distance. And this will be half of the diagonal, I believe. So this will be a square root of 2 divided by 2. Yep. This is a square root of 2 divided by 2. So in here we'll end up with 1 divided by 6 MA squared plus 1/2 MA squared. And this is, I believe, 2 divided by 3. Yes, I think so. So our momentum after is 2 divided by 3 MA squared omega 2. Yeah, that's it. So now let's equal these two things to each other. So we have 1/2 MV0 0A, and this is equal to 2 divided by 3 MA squared omega 2. Let's simplify some stuff. M can be simplified, A can be simplified, and we end up with V0 that is equal to 4 divided by 3 omega 2A. Or we can also express omega 2 as a function of V0. I don't know which one will be useful for us later. Let's have them both. Okay. How about questions? I don't see any questions. So right now we ended up with the situation right after the impact. Okay, so this omega-2 will be omega experienced by our system after the impact. Question to you, is this what they ask us for? No. They ask us to find what is the minimum value of this V0 to reach conveyor C, right? Okay, but we know what happens after the impact. Yes, right after the impact. And now our body will keep rotating, yes? So I think that there will be like some change in the elevation of the center of mass. So question to you, shall we continue this problem using angular momentum or maybe work energy? I think work energy, yes? So second part of the problem is work energy. Second part, work energy method. Okay, so let me draw two configurations, yes? Configuration at the beginning and configurations in the end. Config 1 and config 2. Of course, I was joking. I'm still the one from the previous part of the solution. This one is config 1, exactly. But I think I would like to ask you for some help in figuring out what happens in configuration 2. So guys, question to you. They told us that in the end, our box will be in such configuration. Do you think that this is the configuration we should go for? Somebody says no. So I'm going to give you second choice, okay? Because there's also such configuration to consider. Maybe such configuration will be better. Which one do you think is more useful for our problem? And why? Exactly. That's the correct answer. Basically, this is like the highest position for the center of mass. And once our box passes that configuration, the gravity will do all the job for us. Do you see that? The gravity will just help us in continuing the motion of the box. Perfect. Thank you. So this is our configuration 2 actually. Okay, guys. So, and I think that you don't mind if I say that that body can stop here. Body stops. I know that it's not true because we just need like very, very small velocity, yes? That body has at that position, yes? So that velocity is that small, we can just assume that it stops there, okay? Okay, guys, so since it's work energy method, I'm just gonna do our routine, okay? T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. And let's find these 5 guys, T1, V1, T2, V2. u-12 non-conservative. Okay, what is T2? 0, but it stops there. How about T1? Okay, body pivots about B, so I can go for this expression. 1/2 IB box omega-2 squared. And I think that IB box was found by us already. Let me scroll up the board. Oh, here. Yep. Omega-2 squared. Okay, so this will be 1/3 MA squared omega-2 squared. Okay, how about V1 and V2? We don't have any springs, so it will be only gravitational. mg times some distance, mg times some other distance, some elevation. Aha. So I think that the elevation we should go for is this elevation here, this red one, right? And I think that this angle is 45 degrees. 45 degrees. So that means that this angle is 60. This angle will be 60. Do you see that? I hope you can see that. So that means that this red thing is a square root of 2 divided by 2 sine 30 degrees, which is a square root of 6 divided by 4 altogether, yeah. A square root of 6 divided by 4. Of course, 16 here. Okay, and the final elevation is here. This is just a square root of 2 divided by 2. Great, 80% of the problem done. And now work of non-conservative forces. I think that there is only one non-conservative force that acts on our system, which is reaction force at point B. So let's write it down. Integral of B dot product with SB. And the final question to you guys. What is the displacement experienced at point B? Is point B going anywhere? Point B is a pin, so this is 0. What implies that work of non-conservative forces is 0 as well. Okay, let's plug everything into our original equation, and we will end up with following thing. 1/3 MA squared omega-2 squared plus mg a square root of 6 divided by 4, and this is equal to mg a square root of 2 divided by 2. Some stuff simplify, this simplifies this and that, a as well, and you guys will end up with following value here. Omega-2 is equal to square root of g divided by a times square root of 3 times square root of 2 divided by 2 minus square root of 6 divided by 4. If you grab your calculators, omega-2 will be approximately 0.533 g divided by a squared. And one last final step is to finding V0, because this is what they ask us for. Let me scroll up the board, because I believe that in here we expressed V0 as a function of omega-2. So I can put it here. So this will be 4 divided by 3, 0.533 GA square root. Grab your calculators and obtain that this final value is 0.711 GA square root. And this is the answer. Okay. I will, of course, hang out for 5 minutes after the discussion. It's 11:50, Jaden, so we have to stop, but I will hang out for a couple of minutes. Okay, everybody, thank you so much for today, and thank you so much for the entire semester.